So in our last video, we were talking about the work done by or on a gas and how those works can be negative or positive, depending if we have a positive or negative volume change. And oh my gosh, so this is a lot to take in, and it's going to take some time and some thought. Now, I want to talk about the first law again real quick. The first law relates these three things. Delta U is the change in internal energy of a system. Q is the heat added, and then W can be the work on or by. They used to write it like this, with it being negative work, like minus W, and now they write it like this. And it's confusing because, like we said, work can either be negative or positive. So you've got to be real careful about what you're saying, right? The bottom line is that if you add heat, this is going to go up. And if you have work done to the gas, right, then the internal energy's got to go up. Okay. Let's take a look here. Okay, this is a little weird because these things are all measured in joules, right? So you have some internal energy of your gas, and that kind of relates to when we were talking about kinetic energy, right? And if you add heat, then that's obviously going to go up. And when you add heat, your temperature will also go up. So there's some things that we can grasp here, right? That if I have a gas sitting in a piston and I add heat to that gas, I will increase the internal energy of that gas. And that is its own thing. Now, if this piston is able to move, and if we add enough heat, this may be forced up, the gas does work, and then it will lose energy at that point. So you got to be real careful about what you're talking about. Okay. Now, we talked a lot about graphing in physics. In Physics 1, we graphed a bunch of different things. We graphed distance in time, velocity in time, acceleration in time. We can graph things, graph force and displacement, all kinds of stuff. So here we have a new type of graph where if you put pressure on the y-axis and volume on the x-axis, you will get a certain result. In this case, work will be the area of this graph, right? This is a square shape, and if you take a width of p and multiply by length of v, p times v is work. So the area of what's called a PV graph will tell you things. These are a big topic. Let's just discuss real quick. So what's going to happen is you're going to be confronted with graphs, and they're going to ask you questions, right? So maybe this is the picture of the gas inside of the piston, right? And so they're going to say something like, all right, let's say the gas starts at state 1 here. They're going to use the word state, as in it has certain defined pressure, volume, internal energy, things like this, right? And so they say it's going to start at state 1, and then we say that we're going to move the gas from state 1 over here to state 2. And there's some conceptual things that I can ask, right? So what's happened here? What have we done to or by this gas? Okay. Well, going from state 1 to state 2, the pressure stays the same. This point here you don't move up or down on that y-axis, so pressure is constant. What has changed is you now have a volume that has gotten bigger. So what's happened here, right? Our pressure stayed the same, but our volume got bigger, right? So we had our gas, right? It was right here. Pressure stayed the same, but volume got bigger. So what happened? Well, what happened is that the gas forced the piston up, okay? Volume got bigger. There's more room now, so the pressure stays constant. What do we have to do in order to get the gas to do that? Is we had to add heat. Heat it. And so you can say, all right, from state 1 to state 2, this is what happened. Okay. The work done would be the area under that curve. So you could find this area here, and that's your work done. And what if we're at state 2? we say, all right, let's take the gas from state 2 to state 3. What's changed? Well, we have a big drop in pressure. Volume stays constant. So we have this picture right here. So the volume stays constant, which means this piston doesn't move, but pressure drops. So what do you have to do in order to have a pressure drop, but have the volume stay constant? What does it mean to have high versus low pressure? Well, right now you have high internal energy, right? Because you got all those suckers flying around in there, all of those little molecules. If pressure goes down, that means that we need to get this gas to not be as energetic, right? So what we're going to do is we're going to cool it off. We'll remove heat. Volume stays constant. Now, if I ask you to calculate the work done, this is very fast and easy to do. There is no area under this curve. This is a vertical line. The area there would be 0, so there's no work done. And that's pretty quick. Now, what if we go from state 3, take the gas to state 4? Well, what's happening here is pressure stays the same, and our volume drops. So what does that mean? I gotta erase these suckers. What does that mean? So yeah, if we go from state 3 to state 4, go from here to there, volume drops, right? So it's like we're here, and then we push the piston back down, so we get a smaller volume, right? But how can we do that and keep pressure the same, right? If we force this down, you're compressing that gas, right? It has less space. You're going to increase all of the internal energy of all of the molecules. So how do you do that? How do you keep the pressure from going up? Well, you got to cool it, so you got to remove heat. If that makes sense. And then finally, if we go from state 4 back to state 1, what's happened there? Well, now volume is constant, so it looks like this. Pressure increases. How do we do that? We probably had to heat the thing, right? And so you can go around one way or the other way, and this is the kind of conceptual thought process that you may have to take in order to answer some questions. And then I can have you calculate the amount of work done, right? Which would be the area of that shape. It probably will happen that you will either have pictures that are something like this square here, or you may have pictures, maybe something starts here, maybe ends up here. What in the world is that? How's that working? Let's do this. Maybe you have a straight line here, right? And then maybe this is what happens where you go 1, 2, 3. So you probably have shapes that are either square shapes or they're triangular shapes, right? And the reason is because we can find areas under the curve of those shapes. There are instances where a gas maybe starts at a state here and ends up at a state here, and it goes like this. Something like that. It's a curve. And to find the work done, it would be the area under this curve, right? The only problem with that is that's this wacky shape. And what you're really doing is you would have to break up, like this is volume and this is pressure, right? So here, it works because you have this square shape. I could even take this and just break it up into tiny little square shapes, right? A lot of small little square shapes. I can even make these smaller. Those of you who are taking calculus are starting to go, wait a minute, I could break these into infinitesimally small little tiny little rectangular shapes, right? And what we're really talking about is something called integration. And we wouldn't need that for this because this is this nice defined shape. Same thing here where we have all of these. We can break this into all these little pieces. Something like this, you would need calculus, is why I brought integration up, in order to solve the area under this curve. So you probably won't see curves like this. You may be asked to just define what is the process. So if I have a graph that goes like this, and I have two states, and it goes like that. It's a curve. You probably won't be asked to find what is the area under that curve, but you may be asked to say what's going on here. And that's a conceptual thing that you probably can do, knowing this. So here's an example of a problem. The gas does work and expands, so it starts here. We'll call that state 1, and it goes to state 2 right there. The gas does work and expands from a volume of 1 to 3. Pressure stays constant. And they're using atmospheres here. Usually you don't see that. Well, you can. You can see that, or you can see pascals. It all depends on the problem. So how much work is done from here to there? Right? Well, work is equal to PV. Okay. There is a positive volume change. So what's happened is the piston has been forced up. Now, I need to add a little minus sign here because this is work done by the gas. And remember, we said that when work is done by the gas, we have a negative because the volume change is positive, right? Volume gets bigger. The piston is being forced up. But there's a little minus sign here. So when you take that positive volume change and multiply by that little minus sign, you get a negative. Okay? So that's a thing. And so you can just take this, which is 3, and multiply by 3 minus 1, right? It's actually 0.001 and 0.003. And you'll get the amount of work done. Going to the left, you'll get a negative because it's work done by, going that way. Okay. Then at state 2 here, we then take it to state 3, right? In order to do that, we would have to cool it off. Pressure decreases, but volume stays constant. And there is no area under that curve, so the work is 0, right? The gas is then taken from this point here and goes to here, right? The gas has been compressed because volume goes from 3 to 1, so we're squeezing that gas. And so what happens is you have a negative volume change. When you take that minus sign and multiply by that minus P, you get a positive answer. When you go from left to right, you get a positive. So what we say is we've done work on the gas from here to there. And then we go from here back to here. I think this is from state 4 to state 1. And the gas is heated up. Volume doesn't change, but pressure goes up. And there's no work done because there's no area under that curve. So there is no PV, right? There is no change in volume. It's 0, so there is no work. So I hope this process makes sense. Okay. What is the net work? The net work would be the area inside that shape. Okay. Going to the right means you have positive, and going to the left means it's going to be negative. So this is a thing. Here's a little example problem, and I think I've done all my numbers right, but leave it to me to screw something up. So what they're telling us is that process AB, so going from here to here, adds 150 joules of heat. Okay, there's no volume change, it's stuck at 2. And then they say for process BD, okay, the gas does work. How do we know? Well, there's a positive volume change from 2 to 5. And in that process, you get 600 joules of heat. So AB is 150, boom, boom. BD is 600, okay? So we get a total of 750 if you add those two up. And so here's what happens. The work done from A to B is 0 because there's no area under the curve. To get the work done from B to D, you would have to calculate that area under that curve. This is 8, right? And then you have a change. 5 minus 2 is 3. 8 times 3 is 24 times 10 to the 4th, right? And these are times 10 to the minus 3, so you end up with 240, if that makes sense. Can you fill in the rest of this chart, pause it, and try? Give it a shot. Answers.